Hello, my name is Jeeho BYUN, and I'll be presenting a lecture about figures inscribed in circles and related geometric lemmas. So today's lecture is aimed to explain geometric concepts in an understandable and easy to remember way, complete with proofs, and as well as introduction to commonly used geometric lemmas and answer any previous questions people may have had about these theorems, even if they already knew them. So first of all, properties of cyclic quadrilaterals. This is a pretty commonly known one. CAD plus CBD is the same as ACB plus ADB, which is equal to 180 degrees. AC plus BD is equal to PQ, or CD times AB. This is known as Ptolemy's theorem. And if we denote the intersection of AB and CD as X, then AX times XB is equal to CX times XD. And this holds even if X is somewhere outside of the circle and intersects the circle at 2 points. And this even can be inverted in a way to prove that A, B, C, D are concyclic if this powerful a point holds. Also, the next one is that if a trapezoid is inscribed inside a circle, it must be isosceles. This is a pretty fast and easy proof with just extension of AB and taking this angle over here. And the last one is Brahma-Gupta's formula, which some of you may know. And S here is the semiperimeter, which is A plus B plus C plus D divided by 2. And this gives the area of a cyclic quadrilateral with sides A, B, C, and D. And then properties of inscribed angles. Angles that originate from the same chord of a circle are the same, like this one and this one. Angles from ABC to AOC, O being the origin, is doubled. This is also a pretty simple proof. So because, for example, you can extend the line like this being theta, and this being theta as well, because due to the radius, this is an isosceles triangle. And obviously, the sum of these two angles will lead to 2 theta. And finally, this is a little trickier proof, but the angle formed between a tangent line and a chord is equal to an angle originating from the chord. And the proof for this goes something like this. As you can see here, TP is tangent to the circle with center O, and TO is tangent to the circle with center P. And if you look at TPQ, we can call this theta. Then because TQ is a perpendicular foot, OTQ is also theta. And if we extend TQ, then the angle that's formed between TP and TQ, namely theta here, theta 2, is going to be the same as this theta 2. Hence, we have the proof. The next geometric lemma that I'll be introducing is a 9-point circle. And this is when these points are the midpoint and the orthic triangle. The orthic triangle is when you have like all the lines needed to form an orthocenter here at H. And this will be the orthic triangle. And this these will be the midpoints. And what is the proof for this? To do that, we need a circumcircle. And also, we need to prove that when H is reflected about, let's call this point A, B, and C, then when H is reflected about BC, it is exactly on the circumcircle. The reason for this is that if we call this like H prime, then the angle from BH to C will be the same as BAH. And because this is a right angle, this angle is going to be the same as this. So we have alpha, and then due to BAH being the same as BCH, we have alpha here as well. And HH prime is perpendicular to BC, and the angle is are the same, which means we have a congruence. And thus, these two sides are the same as well. This lemma is useful whenever orthocenter and a circumcircle are mentioned together. And, oh yeah, I didn't do the proof yet. So if we think of bringing all the points on the circumcircle as 1/2 times closer to H, then H will be on BC. And the midpoint as well will be on BC. And this naturally will be half of HB. It will be the midpoint of HB. Same for all the other circles as other points as well. And now we see that this circle is like a homothety from the circumcircle of ABC. And because the center of the circumcircle, here we have O, it was also brought like 1/2 times closer to H. The center of this circle is going to be the midpoint between O and H. And here we have the 9-point circle. Yeah. Now the next one is the in-center/x-center lemma. First, for people who might not be familiar with the term x-center, it's when the two bisectors of the external angles meet an internal angle bisector. And an interesting fact here is that when the extension of A and the incenter meets its circumcenter, this point, I prime, will be the center of the X circle. And the reason for this is that if we want to show that this is a circle, we have to show that I prime, let's call this D, DB is the same as DI and DC. The way we show this is by finding the angle of IBD and showing that it is the same as, let me just erase the annotations because it's kind of getting in the way. We want to show that DBI is the same as BID. Now, how do we do this? We can think of DBI as being divided into two angles, DBC and CBI. But because DBC is inscribed inside a circle, it is the same as DAC. And because this is the incenter, this angle and this angle are going to be the same. So IBC is going to be the same as ABI. And for the same reason, DAC is going to be the same as BAD. So we have that DBI is the same as these two angles together. And obviously, because AD is 180, AD is just a straight line, these two angles will meet here, and the sum of these two angles will become BID. Hence, we have the proof. Now for some example problems. This is a pretty easy one, so I recommend trying it. Here's the diagram. I think about like 1 minute and 30 seconds should be sufficient. Okay, so I think most people would have tried the problem by now. So I'll show you the solution. This is a solution using the theorem we introduced earlier, the power of a point theorem. In the problem, it gives us that DE is equal to 3 and EB is equal to 5. And now immediately it sort of like looks like a power of a point because we even have EC, it's 1. And then how are we going to express EO? Well, it's simple. It's R minus 1. And O and the extension of EC, let's call this like K. Okay, is going to be R. And hence, we have the equality 1 times 1 plus 2R, or EC times EK is going to be the same as BE times ED, or 5 times 3 equals 15. And now we can just solve for R and find the radius of the circle. Now the next one is a little bit harder, but nonetheless pretty doable. So take a gander. All right, so I think everyone tried it. So for the solution, this is going to be the diagram. Here we have omega 1, or I don't know how to pronounce this, but I'm just going to call it omega 1 and omega 2. And here we have A and B, the common external tangent. One thing we noticed right away is that since we want to prove that this bisects this, we can set this as equal. And then due to power of a point again, if we call the midpoint of A and B X, we want to show that it's going to be on the radical axis or the common chord of omega 1 and omega 2. So AX squared is going to be the same as power of this circle, or this times this, where it intersects the first time and then where it intersects the second time. Or no, this times this, sorry. Yeah. And then it's going to be the same as the power of this circle as it is for point X, because this circle also intersects X, the like extension of X, at this times this. So it's gonna just be the same as XB squared. Yeah. So since AX squared is equal to BX squared, and they're both lengths on a Euclidean plane, AX is going to be equal to BX. Here's a similar problem. And if you want, you can like take a screenshot if you're watching this in a video. But if you're in real life and you would like to try this problem, I'll email it to you if you want. Now, for the last problem, this is a bit of a tough one, and it's probably understandable even if you don't get the solution right away, since there is a bit of like calculation to be done, even after using the theorem, so it doesn't die right away. Also, just a hint, but a common way to use like Ptolemy or power of a point is by finding lengths that can be expressed in terms of like one variable. So in this case, it could be like the length of the square, since AC can also be expressed in terms of that. Okay, so let's go over the solution now. We start by noticing that AC and BD are both the diameter of ABCD, since this is a square and these are going to be right angles. And as I said before, we have the idea of expressing these lengths in terms of the same variable. So we're going to let the length of the square be x. Looking at cyclic quadrilaterals APBC, so this one here, we're just trying to include as many like lengths in terms of x as possible. APBC and ADCP. It doesn't necessarily have to be these two cyclic quadrilaterals too. There are others that work. ADCP. And now it is evident that PB times x squared root 2 plus PA times x equals x times PC. So that's the one we got from APBC. Since x times PC is going to be equal to PA times x plus PB times x root 2. This, if you remember, was a Ptolemy's theorem that we covered before. And in a similar way, we just do the same thing for the other quadrilateral, ADCP. AC or x squared 2 is going to be the same when multiplied by PD is going to be the same as AD or x times PC plus PA times DC or x again. Now we just solve the system of equations using these conditions to find the answer. Yeah, and that's it. Thank you for listening.